Okay, seeing like everybody's starting to come back. Welcome back. Okay, so this range over here, I guess yellow is still visible. This range in set builder notation will be the set of all x such that x is less than or equal to 7, but greater than or equal to 0. Okay, so now let's apply this to our function f of x is equal to x squared minus 1. What's the domain? Well, can anything we input into this function mess it up? What if I plug in negative numbers? The square will just make a negative times negative a positive, okay? What if I plug in positive numbers? Okay, nothing, it'll just output a number, so nothing we do will mess this up. Even if I plug in 0, it's just 0 squared minus 1, which is 0 minus 1, which is just minus 1, and that's a valid value. So because of the fact that any input into this function causes an output that is not either undefined or complex, we said that the domain is all real numbers. And in set builder notation, it's the set of all x such that we say x is an element of the reals. But what about the range? To see where the range of this function is, it's helpful to graph it, just like it was over here, to see a visual graph. Because we want to see how much y does it encompass. Okay? So the way we graph things is we create a f of x table. And we pick some symmetrical values about the origin. Let's pick, our favorite -2, -1, 0, 1, and 2. And let's see how f of x responds. Notice that f of -2 is the same thing as -2 quantity squared minus a 1. Notice that's the same thing as a 4 minus a 1. Okay, so that means over here we get a 3, because that's what 4 minus 1 is. What's f of -1? Well, that's -1 squared minus a 1, which is just 1 minus a 1, which is 0. So I go over here and I put a 0. What is f of 0? Well, that's just 0 squared minus a 1, but that's just 0 minus a 1, which is minus 1. What is f of 1? F of 1 is 1 squared minus 1, which becomes 1 minus a 1, which is a 0. And last but not least, f of 2 is equal to 2 squared minus a 1, which is the same thing as 4 minus a 1, which is the same thing as 3. So I put a 3 here. And I forgot to put a 0 over there. Okay. So we still are yet to determine what the range is. We figured out the domain is all real numbers. Hence us plugging in numbers and nothing messing up. But now let's graph what we have so far. And I will use only white so everybody can see. All right, let's go with -2, -1, 1, 2. All right, and then let's go with 1, 2, 3 on the y-axis. Here's the x-axis. I go to -2. I find a +3. I put a dot. I go to -1. I find a 0. I put a dot. I go to 0. I find a -1. I put a dot. I go to 1. I find a 0. I put a dot. I go to 2. I find a 3. I put a, guess what? I put a dot. Okay. So then what we do is we connect the dots. So we get this shape here. This shape here is called a parabola. Is everybody in here? Nobody said anything in the chat. Can everybody see our graph? Okay, good. Okay, good. So what is the range? The range. The range is the y value that this thing ranges through. So from here, notice the y values range from here to here. Can you see the yellow? Notice that they're headed towards what? Positive infinity on the y-axis. And notice that they cut off right here at this -1. So we may assert that the range, I'll put it as R, in arrow notation is equal to -1 included, all the way to positive infinity not included. Easy as that. So now we've determined the range of f of x is equal to x squared minus 1 because we tabulated some inputs and outputs, put a dot, connected the dots, noticed visually that, hey, this function has the smallest output -1, and all of its other outputs head towards higher and higher values. You see that? Following these outputs right here. What was the domain? All real numbers, because you can plug in any number and the function will evaluate it. There's no dividing by 0 and f of x is equal to x squared minus 1. There's no square roots causing a complex number. There's nothing to mess it up. So all real numbers works for it. Does that answer your question? Gilberto? So visually, what about a function like this? What is the domain? What is the range? Seems like any input causes an output, so the domain is all real numbers. Furthermore, if we look at the graph and see where it ranges, clearly it ranges from all the way down here, all the way up here. So it must be true that also the range is all real numbers. So now let's talk about piecewise functions. Let's talk about piecewise defined functions. A piecewise defined function, f, is a function that's literally defined into pieces. It's defined in pieces. So for example, we say, let's say f of x is equal to 2x plus 1 if x is greater than or equal to 0, all right? But it becomes negative x if x is strictly less than 0. We have defined a piecewise defined function. It's a function whose domain and range is partitioned into pieces. Let's graph this, because what we really want to know is, what is the domain of this thing? And furthermore, we want to know, what is the range of this thing? Utilizing the principles we've already established about linear equations, we notice that this is a linear equation. Y is equal to mx plus b. Our b is our y-intercept, that 1. That means over here at 1, our line is going to cross the y-intercept at 1. Furthermore, this equation implies that the slope is 2, meaning change in y over change in x is equal to 2. Meaning, let's say I'm at here. 2 is rise over run, meaning I rise by 2, 1, 2, and I go over by 1. Same thing, rise by 2, 1, 2, go over by 1. So I need to put a 5 up here. You guys see that? Furthermore, it's drop over run. So I also have to drop 1, 2 over here. Boom. Okay, so I can connect the dots here to form a line. And our lines should be going through our points if we draw them nicely. Okay, but look, it says if x is greater than or equal to 0. So I've actually gone beyond what the piecewise defined function allows. It doesn't allow for this function 2x plus 1 to model our function past to the left of 0. It can only define the function from 0 and to the right. So what I'm going to do is I'm going to delete this till there. Boom. After here, to the left of 0, for inputs x are less than 0, it needs to behave like a negative x, okay? And so since this is not equals to, I'm going to put a hollow dot over here. Why did I put my hollow dot over here? And why am I now drawing the rest of the graph like so? It actually might be helpful to do this in a different color. Why am I drawing that like that? Well, it's because this is a line, y equals mx plus b. It has y-intercept equal to 0 because b, there is no b. That means the y-intercept must have been equal to 0. And the slope, m, is a negative 1. And so it drops 1 and goes to the left by 1. It drops 1 and goes to the left by 1. It drops 1 and goes to the left by 1. The open dot is not a part of the equation, right? Oh, okay. So the open dot means that yellow line doesn't really touch the origin. It gets close to it, but it doesn't touch it. Because our piecewise defined function says, oh, x is less than 0, but not equal to. So because it can't be equal to it, it's got to be an empty dot. But notice x is greater than or equal to 0. I put a solid dot because it actually does equal this spot. So we fill it in. We fill it in because it actually does equal that spot. Because x can actually equal 0 and output what is f of 0. If this is my f of x, f of 0 is determined by this function. And that's why we put a solid dot at 0, 1. But if I wanted to know what is f of, let's say, -2, the piecewise defined function has to use this. So then that means this becomes -2, which is actually +2, okay? Which actually means I drew this actually wrong. This needs to go the other way. I'm glad I actually did that. Because take a look. When I'm at -2, right here, the function should be spitting out a +2, because a negative is a positive. So over here, it should be right here. -2, +2, put a dot. -1, +1, put a dot. And clearly, -3, +3, put a dot. What I mean by that is clearly f of -3 would then equal negative of -3. And you guys know a negative is a positive because the opposite of right is the opposite of left, which is right. Yeah, so I actually drew it wrong, and I'm glad that I evaluated it for some points, because it should look like that. So what is the domain and what is the range? Well, the domain, we notice that the domain, this function is defined for all real numbers. Because anything to the left of 0 is defined by the yellow, and anything at 0 and beyond is defined by the white. What is the range? Well, we notice that the function ranges from 0 and it goes up. Okay. We notice that the yellow function has range, a slightly different range. Range of the yellow function is from not included 0 to infinity, whereas the white function has range included 1 to infinity. Does that make sense? How's it look? Does that look better? Did I make the view better by doing that? That's good. I just wiped some of the chalk dust off of the lens. Did that improve it drastically? Very clear now. Awesome. Those particles, those dust particles were causing the light rays to refract and not be focused on the lens. Very good. Very good. Once in a while, I should do that. Okay. So let's do one more piecewise function, and let's define it in 3 pieces now. Let's have a field day here and define it in 3 pieces. And then we got to move on to 3.3. Let's get a piecewise defined function. Let's say f of x is defined piecewise like so. Let's say that it equals 2 if x is greater than or equal to 5. Let's say it equals 2 over 3x plus 3 if x is less than 5 but greater than or equal to -1. And then let's say that the function equals -5. Actually, let's say -3 if x is now less than -1. So what have we done? We've chopped up the real line into 3 pieces. So this is a 3-pieced, piecewise defined function. Here's our x, here's our y, all right? Let's start from right to left. On the far right, let's go to 5. We got 1, 2, 3, 4, 5. Okay. All right. Then we say, okay, from x equals 5 and on, like 6, 7, the output of the function is f of x is equal to 2. 1, 2. So that means from 5, I go to 5, I find 2, I put a dot. And what kind of dot? A full dot. Why do I put a full dot? Well, it's because it equal to. 5 is greater, x is greater than or equal to 5. So that means this function is constantly equal to 2 forever towards the right, towards positive infinity. Now, what about, that was the first piece, piece 1. Piece 2, now it's saying that the function is 2 over 3x plus 3 when it's less than 5 and greater than or equal to -1. So I put my -1 here. I notice that that is the equation of a line. Y equals mx plus b. Mx plus b. So I realize that our y-intercept is 3. So I know that the line crosses 3. Okay? It touches 3. But what is the line equal to at the other spots? Well, that 2 over 3 gives you rise over run. It says for every 3 you move over, 1, 2, 3, you move up by 2, 1, 2. Okay, I'll bring this up here. 4, 5. Okay. So this needs to move over a little bit so it's right over 5. It was kind of encroaching on the other value here. Over here. So what is it at 4? All right. And what is it near 5 but not actually equal to 5? Okay. Well, near 5, or let's even say actually at 5, what is it? 2 over 3 times 5 plus 3. Okay, so that becomes 10 over 3 plus 3, which becomes 19 all over 3. Because I multiply top and bottom here by 3 over 3, so that becomes 19 over 3. What is 19 over 3? 3, 6, 9, 12, 15, 18. So something like 6 point something. 6 point something. So around here, it's going to approach 6 point something. So like right here, but remember, it doesn't include it. So I'll put a circle, a hollow dot. Near 5 or at 5, it doesn't include the point, but it's somewhere, something around 6 point something. I can just calculate that real quick. What's 19 over 3? It's like 6.3. So this is all the way up at 6.3. And then we just connect the dots. Okay. We want to know, well, what is the function at -1? Well, also we can say f of -1. That's equal to 2 over 5 times a -1 plus a 3. Notice this equals a -2 over 5 plus a 3. Okay. I have to multiply top and bottom here by 3, top and bottom here by 5. So I get -6 plus 15 all over 15. Just multiplying, getting a common denominator. So notice this becomes 9 over 15. 9 over 15 is approximately, it's approximately 0.6. Okay, so at -1, it's approximately 0.6, just a little above halfway, and it includes it, so we put a solid dot. Okay, and then we connect the dots. Notice that over here, this connects like that. It doesn't look like a line, but it should. That's terrible. It doesn't look like a line, but it should, okay? That's a straight line. I know it looks terrible, horrific. And then from -1 to the left, it becomes a -3, but it doesn't include it. So this becomes a -1, -2, -3. And from -1 on, not inclusive, we put a dot here and we move to the left forever. So this is a piecewise defined function defined in 3 pieces. Okay. Moving on to chapter 3.3. Let's talk about the rate of change. Of a function. New chapter, new concepts. The rate of change of a function f of x from some x1 to x2 is defined as the rate of change. I'll call this rate of change R. R is going to be equal to this, f of x2 minus f of x1, everything divided by x2 minus x1. And if you guys notice, this is really the same thing as slope. Why is this the same thing as slope? Because this is the same thing as y2 minus y1 all over x2 minus x1. Okay? But the difference here is that we can apply this to things that aren't necessarily lines. They don't have to be lines for this to apply to them. We can apply this concept to things that don't necessarily have to be lines. So, for example, let's find the rate of change of our parabola. Let's say our function is f of x to x squared, our beloved parabola. And then let's say we want to find the rate of change or the average rate of change from x1 is equal to 2 to x2 is equal to 5. Okay, what is the rate of change? R, the average rate of change. That's our f of x2 minus f of x1, everything divided by x2 minus our x1. Notice that this equals 5 squared minus 2 squared, everything divided by 5 minus 2. So let's compute what this really equals. This equals 25 minus a 4 all over 5 minus a 2. Okay, so this becomes 21 over 3. Which is beautiful because 21 is 7 times 3, right? I can cancel out the 3's to get a 7. So this is the average rate of change of the function f of x is equal to x squared from x1 is equal to 2 to x2 is equal to 5. Does that make sense? Okay. Let's do another function. let's do f of x is equal to the square root of x plus 1. If x1 is equal to 8 and x2 is equal to 24, what is our average rate of change r? Well, it's our f of x2 minus our f of x1, everything divided by x2 minus x1. Okay, notice that this gives us, this is equal to the square root of 8 plus 1 minus the square root of 24 plus 1, everything divided by 24 minus an 8. What does this equal? Okay, well, oh, did I put a 9 here? This needs to say 1. Huh. Okay. That's an error. That should say 1. Okay. So then notice that this equals the square root of 9 minus the square root of 25. Everything divided by, oh, that one's hard. 24 minus 8. That becomes 16. Right? Yeah. So then over here, this decomposes to 3 minus a 5. Everything divided by 16. Notice that then this decomposes to negative 2 over 16, which this is the same thing as a negative 1 over 8. Because 16 is 2 times 8. So our average rate of change of f of x is equal to square root of x plus 1 from 8 to 24 is this value right here, negative 1 over 8. 4 minutes. Okay. Does that make sense? So let's talk about local minima and local maxima. I'm just going to draw some arbitrary function, meaning just something I made up. Just going to make this up here. Okay. What are the local maxima? Are regions of peaks. Here's a peak. Here's a peak. Here's a peak.